Hey there, my name is Chris, and in this video, I'm going to be showing you how to capture audio in C++. This is going to be a bare bones tutorial where I will show you how to set up a basic stream where you can listen to input and display it in the terminal as a bar. Here is the output of our tutorial, and here you can see that it's capturing the audio data that's coming from my microphone in real time. Now my microphone is mono, and so this bar is just straight like that. But if I were on an actual Linux machine, not in the Windows subsystem for Linux that I'm in, then I have access to different devices. And so if I'm playing a song on that device, then I have the potential to actually listen to it here. So you can see that there are left and right channels, and it's reacting to that song instead of my voice. Now you'll have to trust me that it's playing. I don't want to get a copyright strike for this, but essentially that's what it outputs. All right, so let's jump into the tutorial with a blank project and get started. So I'm starting off here with an empty folder called CPP Audio Capture, and I'm going to start off by making a main.cpp. This is going to be our source file and where we're going to do all of our coding. Let's start off with a simple main function. So I'm going to do int main. And here I'm just going to return. First I'm going to include standard lib so that I can return exit success. This actually expands to 0, but it's good to have this here, and we'll need standard lib for other functions in this program. We can also just test if this is working by including standard io.h so that we can put a printf here. And so now if we compile and run this program, we'll see hello world and it will terminate. So if I open the console here and I do g++ -o cpp audio capture, and then I have my source file, which is main.cpp, then we see this file appear here. And now if I run cpp audio capture, I'll get hello world and it exits. Perfect. Now we're going to be installing and including some libraries here. So let's add a make file to make that process really easy, so that instead of remembering all of these commands and having to run them, especially when we have more files in here, all we have to do is run a make target and it'll all happen. So the first thing we'll want to do is have a make target for our executable. And this will do g++ -o. And I'm going to use this variable here. This variable in a make file is equivalent to whatever file we're trying to create. It expands to that. And then this will rely on main.cpp, and the source files can be included here. So this expands to whatever the dependencies are. It makes it very succinct and easy to manage. We can test this again by running make cpp audio capture. It says it's already up to date because we haven't changed our file. But if I change the file and run it again, then it will compile it again. And I have my binary. Another thing we can go ahead and do is set up a clean target that will remove cpp audio capture. And since we're using this in multiple places, we can make this an environment variable so that if we want to change the name of our executable, we can just change it in one place. So if I do make clean, it'll remove that. If I do it again, the reason I put -f here is so that it won't error if the file doesn't exist. And then if I make cpp audio capture, it'll go ahead and do it. All right, so now we're going to set up the make file targets for importing our library. The library we're going to be importing is PortAudio, and to get started, we're going to need to make sure that we have a few things installed. I'll include this command in the description, but we can do sudo apt-get install, And we're going to need curl, cmake, clang. These will be for installing and downloading the libraries. We'll also need pulseaudio, libasound-dev, and libjack-dev. So I already have these installed, but if required, hit enter when it prompts you for a yes or no, and you will have all these installed. So now we can go into here and set up a makefile target for installed deps. So this is going to be dependencies. Also here, clean is not an actual file, so I'm going to declare it phony. This we can leave as is because it is an actual file that we're creating. This as well, we can make phony. Install deps does not rely on anything. First thing we can do is make the directory lib. We're going to store our library in a lib folder. The -p is just going to skip creating this if it already exists. Then we can curl the link to the library that I will include in the description. This is the library tarred and compressed. And then we're going to pipe that into a command that extracts it into the lib folder. Then we're going to cd into the file that it creates, and then run the installation steps that PortAudio requires. So we're going to /configure. This will be within the lib PortAudio folder, and it's going to run the cmake steps that it has. And then we're going to, in that same folder, make -j. -j will run it multi-threaded, so it'll be a bit faster. So ultimately, what this whole thing is doing is it's making a lib folder. It's creating the PortAudio folder inside of it by extracting the file here. And the reason that we're piping curl into this tar extraction is so that we don't actually save this file into our file structure. All it's doing is piping what this contains into this tar. And then in here, we have to have double ampersands because a make file, if you just cd and then press enter, it'll forget that it was in this folder, and these commands will attempt to be run in this directory where none of the files will be. So if you cd into there and then double ampersand these commands, then they'll happen in that directory. So let's try this. We're going to run make install deps. So here it's downloading it off the internet. That's what the curl is doing. And you can see it has already already made that lib. So now it's running /configure and make. And all of this is just happening within this folder. That's a good thing about the make file, is that all this can just happen and we can sit back and watch it, and we don't have to worry about this configuration again. While this is installing, we can also make an uninstall target in case you want to remove these. So first thing we're going to want to do is cd into lib/PortAudio, and then PortAudio has an uninstall target. So we're going to run that. Now back in our root directory, we're going to remove recursively lib/PortAudio. And this is going to be in an uninstall deps target. And this is also going to be phony, since uninstall deps is not a file that we're creating, it's just the name of a makefile target. So if we were to run this, it would remove all of this and uninstall it first. Okay, so the last thing we'll do in this makefile is include the libraries that we need to. In this case, that's going to be PortAudio. So we can declare this clib variable, and clib is going to include all the flags that we need in order to include our PortAudio library into our compilation and linking step. So this is going to be -I for include, /lib/PortAudio/include. This is going to be all the files that PortAudio needs to have available, all the header files. We'll also need /lib/PortAudio/lib/libs/lib PortAudio. .a. This does not have a -i in front of it because this is just a library file that needs to be included. We're also going to include rt, -l a sound, and -l jack, and -p thread. These are what are required for PortAudio to work. And we're going to save that, and then we can include clib in our compilation step. And that is all we need to do. So let's go back into our source file and start our audio capture. So now we can include PortAudio.h. We can use these double angle brackets because of these flags here. Everything that will need PortAudio.h included is going to be in this include directory. So let's remove this printf. That was just a test. And in our main function, we can kick things off with pa error equals pa initialize. This is going to initialize our PortAudio instance. Now this error is going to be kind of carried all throughout these functions. So I'm actually going to separate this out so that we can reuse this one variable as we go. And then I'm also going to include a handler function for what do we do if this error is an actual error. So what we can do is say static void check error. It's going to take in a PA error. And here's the check. If error is not PA no error, then we're going to printf PortAudio error, have a string, and this string is going to be the result of PA get error text of the error. So it'll print out exactly which error we got. Under that, we can exit failure. And we're done with that. So now we can check the error that we get when we PA initialize. So PA initialize is going to allocate some things that PortAudio needs. And before we exit, we need to allow PortAudio to deallocate everything that it needed. And so what we can do is we can terminate PortAudio. This is going to be with the function PA terminate. We can check the error again, and then the function will safely exit. Between here, we're going to include all of the main function code that we need. So the first thing we can do is query the devices that we have. So how we can query our devices is by first saying num devices is pa get device count. This is going to give us the number of devices that PortAudio has available to it. From here, we can just declare how many we have. So we can say number of devices. This is going to be an integer, and we can display num devices. Now, if we run this, first we could do make cpp audio capture. And if we run that, then we'll see a little bit of debug information here, and number of devices 2. Now these are a bunch of warnings. You might get these. If you want to silence these, you can run it by rerouting standard error, which is file descriptor 2, to /dev null. And you'll just get the raw output of standard out. So we can see that we have 2 devices available to us. Now, if we want to see information about these devices, then we can iterate through these devices and get their information. Now, first of all, number of devices can be negative when returned from this. It says that a non-negative value is the number of devices, or it's an error code if it is negative. So we can do if num devices is less than 0, we can printf error getting device count. And then we can exit failure. Otherwise, we are good, and the number of devices is greater than 0. It's a valid number. or it can be 0. If it is 0, so we can say else if num devices is 0, then there's not much that we can do. So we can say there are no devices on this machine. We can say no available audio devices. And then we can exit success because there was no error, there were just no devices. Otherwise, we have devices available to us, and so we can work with this. In fact, I'm just going to press enter here so that we're out of this, so that if either of these two things happen, then it'll exit, but if not, then we are beyond that point. We are here, and so that it'll terminate if needed. All right, so we can define PA device info. Now, what this is going to do is track the device info for each of these devices. We're going to iterate through them. So let's do our iteration. For int I is 0, I is less than our number of devices, I++, then we can say device info is equal to PA get device info of the device. Now the device is denoted by an integer, and so we're going to be using I, and they start from 0. And we're going to need to make this constant. All right, so from here, device info is going to be a struct. And if you control click on this, you can see exactly what this contains. It contains all this information. We're only going to include some of this information in the terminal, namely those things which are actually kind of important. So we're going to printf device %d, and that is going to be I. So we're saying device and then the device number, and then we're going to print out some information. We're going to tab this a little bit so that it looks nicer in the terminal, include our new line there. And we're going to say name is this, and then we can say device info name. And we're also going to include max input channels, max output channels, and device default sample rate. And these are going to be numbers, and this is going to be a float. So this is all the information that's going to be included with each of our devices. And if we run this again, compile first and then run, we'll see the device info that we have for these devices. Both of these are identical. I'm pretty sure default actually just points to the device that we have, and I only have one real device on this machine, and that's Pulse. And this comes from PulseAudio. It has 32 maximum input channels and 32 maximum output channels with a default sample rate of 44,000 Hertz. Now, the number of input and output channels will become more important later, because when we're creating a stream that we can listen to and output audio to and from, we need devices that have more than 0 input channels and more than 0 output channels. Now, if you have devices that have more than 1 input channel and 0 output channels, and you have another device with more than 1 output channel, then you can use that second device for the output. But a stream needs to know that it has input channels and has output channels, at least one of each. So this will come in handy when you are determining which device you want to use. Now for this program, I'm going to be using device 0 because I know that it has the number of input and output channels that I need. So after this, I'm going to say int device is 0. And that is the device that I'm going to be using. All right, the next step is to create a stream. Now an audio stream takes audio input and does whatever it needs to with it and then puts it in the output. It can do nothing or it can do something. In our case, we're not actually going to be outputting to anything, but we are going to be capturing input and displaying it in the terminal. Now PortAudio has PA stream parameters that it uses as input and output parameters for its stream. So we're going to set these up really quick. First, we're going to declare these variables. So PA stream parameters, input parameters, And then we can also have output parameters. Now for the size of these, we're going to null them out. The first thing we're going to need to do is use the memset function to set all the data to 0. For this, you're going to need to include cstring. And we can say memset the address of input parameters to be 0 for the size of input parameters. And now we can set the actual parameters. Now if we control click on this, we can see that this is also essentially just a struct. It has all of these parameters, and so we're going to set these. So we can say input parameters dot channel count. We're going to make this 2. We're going to work with the first 2 channels in this device. These are going to be the left and right inputs. Then I can say input parameters dot device is device. This is going to be equal to 0, and this is telling it that I want to be using device 0 for the input of this stream. Now we can say input parameters dot host API specific stream info is null. We don't need to worry about that. Input parameters dot sample format is going to be PA float 32. Input parameters dot suggested latency is going to be a value that's determined by the device info. So just like before, we can say PA get device info of the device that we're using. In this case, it's going to be 0. And we can say default low input latency. This is going to allow us to kind of run this in real time, which is what we want. And we're done with the parameters. So now we can just copy and paste this for output parameters and set this to be here. And in all these cases, just set these to be output parameters. And we actually don't need to change anything here. Now, even though we're not outputting anything to this device, we're still going to set the channel count to 2. I found that if I set this channel count to 0, it'll actually error at me and say that that is an invalid number of channels. And so that is why we are required to include devices that have one or more of what they're asking for. Now, it's also important to note that you can specify a different device for the output. And so if you have as I was saying before, if you have a device that doesn't have the required number that is more than 0 of an input or an output number of channels, you can try to find another device that does include that and then make that the device that you use here. All right, so now we can finally include our stream. So this is going to be of the PA stream type. We're going to make it a pointer and we'll call that stream. Now we can say error equals PA open stream, and we're going to include all of its parameters. Now it has quite a few here, so I'm going to walk through these one by one. First, we're going to include the address of the pointer of stream. This is in line with what it has here, and this is going to be the stream that we are opening. Then we're going to include our input parameters, of the address of them, and our output parameters. Then we're going to include a sample rate and a frames per buffer. Now up here we can include preprocessor variables in order to define these. So we can define sample rate to be 44,100, and we can define frames per buffer to be 512. This can also be 1024. This is essentially the size of the buffer that we're going to get in our callback function for the stream. It captures the amplitude of our waveform at any given moment, and it does this 44,000 times per second, hence the 44,000 hertz. Frames per buffer is going to say, after I've gotten 512 of these, which is going to be a fraction of a second, take these and pass it to the callback. And that's the data that we're going to have to work with. A higher buffer will mean that we have more data to work with. If we have less, then we're going to go into that callback function more often, and so our display speed can be faster. But for a higher buffer, we'll have more data to work with, and this can come in handy, as we'll see in the next video, with determining the frequencies of a waveform. But for now, 512 is good enough to get good speeds for simple capture of the audio. So back down here, we can provide the sample rate and the frames per buffer. Now we have some flags that we can provide, but we're going to say PA no flag. Next would be a callback function. And we haven't defined this yet. And so above the main function, we can go ahead and define this. So up here, we can say static int PA test callback. And it's going to take quite a few parameters, just like the stream open. It's going to take in a const void pointer to the input buffer. Then it's going to contain a void pointer to the output buffer. Then it's going to take an unsigned long frames per buffer. Then a const PA stream callback time info. It's going to take a pointer to that. Then it's going to take in the callback flags, PA stream callback flags, call that status flags. And lastly, it's going to take a pointer to our user data. Now we won't need to use any user data in this particular program, but as we'll see in the next video, this will come in handy where we can define data that persists between callbacks that we can modify. Here, we can say PA test callback. That's going to give it our callback function. And finally, we would include our user data. In our case, that's null for now because we don't need any. Now, this could have errored, and so we're going to check that error. And now we have opened the stream. Now, before we terminate, we also need to close this stream. And so we can say error equals PA close stream and pass it our stream. And we can check error after that. Now between this, we can start and stop our stream. So when we start our stream, we can say error equals PA start stream and pass it our stream and check the error there. And then we can PA stop stream and check our error there. Now this is going to happen instantaneously and we don't want that. We're going to actually have it sleep for about 10 seconds. So we're going to say PA sleep 10 times 1000 because it takes milliseconds as input. And now it'll start the stream and capture audio for 10 seconds and then stop the stream, close it, and then terminate, and we will exit. So essentially what this will look like is the moment we run the program, there's going to be 10 seconds of audio capture. As we'll see in the callback function, we will be able to visualize this audio capture. If we don't include anything in our callback function and we just compile and run it, then it'll just wait here for 10 seconds. Now we didn't return anything from this, and we will. We can actually just return 0 to tell PortAudio that there was no errors. And we can see that it was capturing audio. What it's actually capturing here is my microphone. So once we define how we're going to visualize this audio data, then you'll see that as I talk, it reacts in real time to what I'm saying. So now we can, inside this function, start our callback. Now, variables that we're not using, we can go ahead and cast as void so that we don't get any errors. If we were to compile this with all warnings, then we would see that it would not like that we're not using the output buffer. So I'm going to cast that to void to avoid that. Then the input buffer is a void pointer, and we want to make sure that we know that this is a pointer to floats, because as we defined down here, we are capturing audio as 32-bit floats. And so we can say float input buffer. We can just say in here so that it's a little shorter as we're writing code, is the input buffer cast to a float pointer. So essentially what we're going to do here is print out a sequence of characters. Now we're going to have a left channel and a right channel because we have defined that we're going to be using 2 channels. What this is going to look like here is full block characters being extended up and down according to the volume. And we can separate left and right channels by using half blocks. Now you can use any character for this. I'm going to include the full block and half block characters in the description. It just makes things look nice. But all this is really doing is displaying the audio so that we know it's there, and it doesn't really need to be fancy. But for the purposes of this video, I wanted to be fancy, so we're going to do that. Now let's declare our display size. This is going to be the maximum height of our volume bar that we're going to create. I'm going to say that this is 100. It's going to be 100 characters long. In order to update this line over and over again, we're going to utilize the carriage return character. So we're going to do printf carriage return, which is \r. Now, if we don't print out a new line, which we're not going to do, then the terminal won't actually update until the buffer is met. And the buffer won't be met if we keep setting these same characters. And so at the end of all this, we're going to have to flush standard out. And so that way, at the end of this callback function, it's going to go ahead and display whatever modifications we made to these 100 characters. And at the beginning, it's going to return back to the beginning of this so that we can reprint those characters. All right, so the first thing we're going to do is define our volumes. We're going to need a volume with the left side. We're going to set that to 0 for now, and 1 for the right side. So now we can iterate through this input buffer and determine what the volume of the left and the right channels are. Now, the way that this input buffer works is that it kind of stacks the channels on top of each other. We still capture 512 frames for every buffer for each channel. So that means that the first two elements for this 2-channel input buffer are going to be channel 1 and channel 2 for that first frame. Then it's going to have channel 1 and channel 2 for the second frame, channel 1 and channel 2 for the third frame, etc. So that this input buffer is going to contain 1024, or frames per buffer times 2, elements. So we can iterate through this by saying unsigned long I equals 0, I is less than frames per buffer times 2, because that's the size of our input buffer. We can say that I plus equals 2. Now this is going to go over all of the first channel elements, but in this for loop we can also contain anything that we're going to do for the second channel by making our index I plus 1. All right, so to determine the volume of our left and right channels, the volume is going to be the maximum of the absolute value of the values that we see in the buffer. Because the buffer is a waveform that can go positive and negative, we want to say that the volume of a sample is the loudest it gets in the entirety of the sample. So up here, I'm going to define some basic functions to get the maximum and to get the absolute value. So I'm going to say static inline max. It's going to take in 2 floats, float A and float B. And I'm saying inline so that the compiler knows that if it's more efficient, it'll just stick this code right in place since it's not very long. So we're going to return a ternary expression. Essentially what we're going to say is if A is greater than B, return A. If not, return B. So we're going to say return A is greater than B. If that's true, we're going to return A. If it's false, we're going to return B. And that is our max function. And this is going to return a float. Absolute value is going to work in kind of a similar way. It's going to take one input. We're going to call it abs. And we're going to say A is greater than 0. We're going to return A. Or else we're going to return negative A, which is going to make A positive, since A in this case would have been less than or equal to 0. So in this spot, let's set volume L to be the maximum of volume L and the absolute value of our frame. In this case, it's going to be the input buffer at I for the first channel, which is L. Similarly, if we index at I plus 1, then we can determine that this is our right channel. And so effectively what this is going to do is iterate through the entire buffer. And if it sees any values that are greater than its current maximum that it has among the absolute values of these values, then it will set that volume to that, so that ultimately we're going to have the maximum amplitude of any of these frames in volume L and volume R at this point. So from here, we can define how we're going to display our bar. We can say for int I is equal to 0, I is less than display size, and I plus plus. we are going to iterate across all the characters in that volume bar. Now we can determine which character we are at proportionally by saying float bar proportion is equal to I divided by display size. And we can cast this as a float so that we don't just get 0 all the time. So this is telling us that if I is equal to display size divided by 2, then bar proportion is going to be 0.5. Now our volume is going to be usually values between 0 and 1, and so that's going to mean that our volume bar can go up and down at a maximum of our display size. The way this is going to work is that we're going to print full block characters for all the places where the left and right channels are greater than that character. If the left channel is present at that character and the right channel has already dropped off, then we're going to print the top half of a full block. And if the right channel is there and the left channel isn't, then we're going to print out the bottom half of the full block character. And if none of the volumes reach to this proportion, then we're just going to print a space. So this is what this is going to look like. If bar proportion is less than or equal to volume L and bar proportion is less than or equal to volume R, this is going to be the case where we want to print out a full block character. Now I'll include these characters in the description so that you can use them. And this means that our bar proportion has not reached the height of either left or right channels. Now we can do our half block cases. So we can say if bar proportion is less than or equal to volume L, then we can printf again, and this is going to be the top half character. So this means that volume L has not yet been reached yet, but volume R has. And so volume L is the lone survivor here, essentially. Now we can do this same thing for volume R and make this the bottom half. And finally, if we've reached the end of these conditions, then that means that this character is past both volume L and volume R, so we can printf a space. And this should be it. Now if I run this, all right, it looks like there is an existing function for the absolute value of a float, so we're going to use standard abs for that. And let's try this again. All right, so now as I talk, you can see that the volume bar goes up and down according to what I'm saying. This is my cursor over here, and my microphone is mono, but if I did have left and right channels, then you would see that here. This can be the case if you are outputting audio from your computer. It would show up here as separate left and right channels. Now what I'm running here is the Windows subsystem for Linux, so all it really sees is my microphone. But if I SSH into a Raspberry Pi with Linux on it, from here I am actually playing a song through the Raspberry Pi's speakers. If I run this, then you can see that it's listening to that music and it's playing both the left and right channels. And this is using the exact same code that we used before. It's just that this audio input utilizes the left and right channels, whereas my microphone does not. It's just mono. But here you can actually see that that's the case, and that's pretty cool. All right, so I hope you learned something here. Thank you so much for watching, and I will see you in the next video where we will discuss how to capture and display the frequency data of an audio waveform in C++. See you there.